Assalamualaikum and very good day to all of you. Alright, we meet again here for this topic on thin wall vessel and internal pressure, but the focus today is on heads and closures design. Okay, alright. So this is a topic under EPF 4801 Process Equipment Design for Bachelor Program of Process and Food Engineering in UPM, University Putra, Malaysia. Alright. So, to those that very new with this lecture, I'm Shikin Aziz. All right, and then for the reference of this material is taken from Chemical Engineering Design textbook, which is written by Towler and Sinot. Okay, so for heads enclosure, there are 4 types of heads enclosures. All right, where you can select. All right, the selection of this type of heads enclosures, depending on your needs. Okay, and the strengths that the strength requirement for your vessels. All right. Okay, so why we need to use heads enclosures is basically to enclose our vessels. All right, so these heads enclosures can be used to close either on the top or bottom of your vessels. Okay, so the main types are flat plates, okay, and form flat head. All right, okay, and then we do have hemispherical heads, ellipsoidal heads, toruspherical heads. All right, this sorry. Okay, uh, hemispherical, toruspherical, and ellipsoidal heads is categorized under dome heads, DOME. So this is under categorized dome head. All right. So generally, this all heads and closures, the fabrication of it is either by pressing or spinning. Okay, and large diameters are fabricated from form section. Okay, the form section. So there is some part of a welded joint area. Okay. So for toruspherical heads, okay, head is also known as uh, dish end. Okay, dish end. Okay, it's also known as dish end. And the preferred proportion of dome heads basically can be refer from the standards and codes. Okay, so okay, and then for flat plates, okay, for flat plates, this is generally been used for mainways, okay, mainways, okay, and a channel to cover the heat exchanger, okay, and then and uh, it also there is a type which is flange only heads. Flange only heads where there is a flat ends is known as flange only heads. Okay, the flange only heads are the cheapest. Okay, so basically when I said a flange, all right, a flange is this area. Okay, this is what I mean by flange, this area. Okay, flange area. Okay, this one. Okay, so the flange edge is basically a straight plane. It's in a straight plane where to ensure the weld line is away from the discontinuity point between the head and the cylinder part of the vessel. So the welded line, okay, all right, the welded line. Let me change the color of the pen. Mm, so so this can consider as a welded joint. Okay, so we need to the idea of flange is basically is try to put it away from the discontinuity end. This is discontinuity end. Okay, this one is discontinuity end where it will connect to the main vessel body. All right, let's say here, and then you will have a main vessel body. All right, so this is a main vessel body. Okay, so this it will connect between this. Okay, when you put a cap, okay, something like you put a cap on the main body of the vessel. Okay, so the idea to have a flange is generally to avoid because sometimes the welded part joint, it could be there is some limitation of the strength and the smooth surface of it. All right, so okay, and then the limitation of having of flat plates. Okay, the limitation of having a flat plate is the low pressure. Okay, the low pressure is normally been applied for low pressure and small diameter. This one, right? Low pressure and for small diameter vessels, right? And then for torus spherical, right? So now let's look on the torus spherical. So the torus spherical, okay, this one, the application mainly for operating pressure of 15 bar, up to 15 bar. Alright, it's up to 15 bar. Okay, this one, right. So basically, this is up. Okay, up to 15 bar. So up to operating pressure of 15 bar. So well, the limitation is when the design is above 10 bar, so the cost will be higher. The cost will be higher compared to the ellipsoidal head. Okay, so the common practice is to have ellipsoidal. Okay, most practice people will. Oh, sorry for that. Just want to move this actually. Alright, later I will erase that part. Alright, so the common practice is for application above 15 bar, people will select ellipsoidal. People will select ellipsoidal heads. Okay, and then so and then for hemispherical, so okay, for hemispherical, is considered the strongest shape and is capable to resist high pressure. All right. Uh, uh, Compared to the torus spherical, so it's much stronger compared to the torus spherical. And then, but the limitation is the cost. Okay, cost of forming is higher than torus spherical heads. All right. So basically, the hemispherical head is normally been designed, been used for design the vessel which operate at high pressure. Alright, this is an example taken from the Towler and Sino 2012. Alright, okay, the drawing of the flat ends. Okay, there are several type of flat end. Okay, uh, so there is for the A here we have flange plate, and then we have for B. Okay, this one B is for welded plate. Okay, so we can see from here, where is my pen? Okay, so this is the welded part. Okay, welded plate, this is we call it welded plate. And the C as well is welded plate because it joined a two plate. Okay, from this drawing you can see that it's joined two plate, so there is welded plate. And then for this, we know is known this design type, we call it bolted cover, where there is a bowl here to put a bolt. And then this one as well, another example of drawings of bolted cover. So class, actually you need to detail your drawing. Okay, detail drawing like this example for your closure of your vessel, and then for the or for the heads of your vessels. All right. So so the thickness required for the plate, okay, will depend on the degree of the constraint, okay, at the plate area. So we there is a design equation which is specified by ASME code, all right, and this is the uh, oh sorry, where are you go? Okay. Oh, the pen suppose somehow not okay. It's okay. So this is actually the equation, all right, being used to define thickness, wall thickness for flat ends. Okay, the minimum thickness, all right, the minimum thickness. Try to on my pen. All right, now it's function. Okay, don't know what is happening here. It's okay. So this is the minimum thickness. Right, forget it about that. Okay, this is minimum wall thickness, all right. Okay, and then the C, all right, and for is for the design constant, while for DE is for nominal plate diameter. So C and E can be obtained from the SME BPV code section 8 division 1. All right. So this equation is actually being derived based on the analysis of stress in flat plates. All right. So the normally for flat ends, the how to say, the design will be very thick plate. Okay, will be required for high pressure or large diameters. All right. So you can test this equation later on in your project. Uh, Talking about flat ends, the other another thing of the benefit of having flat ends design is the fabrication cost is low. Okay, so you can see here the maximum allowable stress. There is okay, now it's working. Okay, it's multiply with the joint efficiency, right, to be accurate, right, right. And then so for detail design of the SME BPV code, all right, detailed design of the flat this flat end. Okay, for example like this one. Okay, the value for what these things are, nominal plate diameter, and then like this value, this this can be obtained. Okay, this can be obtained from SME BPV code. All right, so for example like for this A, all right, flange only end. Okay, for this A, for example, like just give you this example. All right, okay, for this design of A, the C, where is my pen? Okay, here, C is equal to 0.17 if the radius, okay, corner radius RC, if the corner radius RC is equal to is not more than it's not more than, so that's mean it's not more than something like this lah. It's not more than 3t. All right, then it said that otherwise c is equal to 0.1, and de is equal to di. All right, so basically this is one condition. If this is not okay, if this is not, then you can go to this. Okay, let's say if your design doesn't meet this requirement, then you can use this parameter, okay, in your design. Okay, so that is how, okay, the information that you can get from the SME BPV code. I'm very sorry I cannot show the example of table here because I don't have that document, but maybe in the future, all right, if let's say you can have access to this, you can have a look on the real table from the SME BPV code or the real requirement. All right, so that is an example. Now let's look for the doom ends. Okay, doom ends. All right, all those. So this for this design, the detailed design of this as well is given in ASME BPV code, and then the code actually covers for the unpierced and pierced heads. All right. So what I said just now is unpierced. Okay. So basically for what I mean by pierced heads, basically for those cap or heads where there is opening or connection. So basically if you have this one, this is denote for a solid, okay, solid design. And let's say you have a pierce, so pierce, you might have a closures, okay, something like this for a manway, or sometimes the closures is for a probe, to insert a probe, or sometimes the closure is just because of the you need to put the how to say a road for the impeller, the road for impeller. So this is categorized for pierce if you this. So but this one, the equation for unpierced equation is more simplified. Is simplified equation. Okay. So normally for pierce, for the pierce for this category, right? For pierce, right? For this category for pierce. Sorry for my drawing. Right. Right. For this category, normally the wall thickness, the head thickness must be increased because you need to increase the strength of the head. All right, due to the presence of the holes, okay, on the heads. All right. Okay. Uh, so now the equation for hemispherical heads, you can use this equation. All right, this is simplified form. Again, remember this remember that. Okay, and then what's next? Okay, then for ellipsoidal heads, all right. SME BPV code specify this equation, and again you must remember that this is simplified equation. Okay, this is a simplified equation. All right, for unpierced heads. Unpierced head is simplified equation. All right. So details for the pierced head, you need to refer other detail of the equations. All right. From the standard or vessel handbook. Okay. Uh, because I mainly use material from the chemical engineering design textbook for this material. All right, so I have some limitation for this lecture note. Right. And then for toric spherical heads, okay, SME BPV code specify this equation. All right, where for this it's a bit differ than previous equation. All right, so previous equation only use pressure initial, sorry, internal pressure, internal diameter, and the maximum allowable stress, and same too with ellipsoidal heads. All right, but for torus spherical, because it's a torus spherical, you must know that torus spherical. Where is my pen? Okay, torus spherical. This one. So set the requirement of RC here. Another parameter, special parameter. They call it crown radius. Okay, you need to know the crown radius. Okay. Then again, this equation is, oh sorry, let me show you here. This is RC. Okay. For torus spherical, this is RC. Okay, to show the radius. Where is the radius? So how to explain the crown? This is the part of crown radius. Okay, this is the part of crown radius. And then the RK here, is a knuckle radius. Okay, is a knuckle radius. This is a knuckle radius. So the knuckle radius is the radius of the torus. Okay, in other words, is a radius for the torus. TORU, radius for the torus. And then the RC is actually, this one is stand for crown radius. O is also is also known as sphere radius. It's also known as sphere radius. Okay, all right. And again, this equation is basically, oh sorry, this equation is basically a simplified equation. Again, this is a simplified equation because this is only can be applied for unpierced heads. Okay, remember class, for your design project, if you have any opening on your heads, you cannot use this equation. You must find another equation, right? But there are some thought that they have been said that for preliminary design, for preliminary sizing, okay, for preliminary sizing, you can assume that you are not your head, there is no joint. Okay, you can use this calculation to for the preliminary sizing. All right. Okay, for conical section thickness. Okay, conical section thickness. Conical section is actually when you have, all right, conical section. Where is my pen? It's somewhere here. So if let's say you have part of your vessel, you need to join with another part of the equipment which is have uh, different, okay, radius or diameter, right? Different diameter. Okay, so basically for this, you need to incorporate where are you? Okay, another section to join. Okay, so this part we call it reducer. Okay, we call it as a reducers. Okay, so when you join a different size of equipment, all right. So this is normally can be found at spray dryers, hoppers, and crystallizer. All right, and at SME, we could specify this equation. Okay, has specified this equation, and then for this you need a half of the cone aspects angle for this calculation. And for this is equation, this is applied for conical section away from the transition. Okay, normally there is a transition. There is transition between the reducers and the main vessel. So, why do we have this? Is due to I think the transition is actually to how to say it, to increase the strength of the vessels. All right. Especially if your vessels is working under high pressure. So, mm, okay. Alright, I hope you understand. But it's okay if you don't understand. You can ask me later. All right. Okay, you can ask me through a WhatsApp, and then through our discussion later on. If let's say we can find a time. We can have a discussion. For online conferencing. All right. Using a Zoom or Google Meet, anything. All right. All right. Okay, class. So that's it. Okay. For this part. All right. So basically, there are a lot of equation for this, but this one is cover only for internal pressure, thin wall, thin wall vessel, uh, under internal pressure. So I have shown you the minimum wall thickness, how to calculate minimum wall thickness for the main vessels, and then for the closures and heads. All right, and then here as well. I hope after this you can decide which is the best for the best design, the best shape for the heads of your vessels. Okay, see you again for the next section. Right. All right, class. Okay, bye. Keep safe, stay safe. Assalamualaikum and a very good day.